Okay, hello all of you. Okay, let us see what is a homomorphic filtering. Okay, see this is a topic in third module. You can see this is your third module. Here we have seen frequency domain methods of low pass filtering and high pass filtering, and the remaining topic here is homomorphic filtering. Okay, that is what we're going to discuss now. So this is actually homomorphic filtering means it is a usual method used in signal processing and image processing to enhance the signals. Like actually the filters we are using here is a linear filter. Sometimes we cannot directly apply these linear filters to certain situations where your domain or where the situation is linear, non-linear. Okay, in a non-linear situation we may have to apply linear filters. In that situation, what we are going to do is we will convert our nonlinear system into a linear one. Then you apply this linear filtering techniques. Okay. So basically here you have a filter. You need to apply that filter to the situation where the situation is nonlinear, but you are converting that nonlinear situation into a linear one. Then apply that filter. Okay, let us see how we are going to do that. Here we consider our illumination reflection model that we have discussed in the first module, which means that an image F can be expressed as a product of luminance and reflectance. Uh, so in a frequency domain filtering, what you're going to do is you will apply uh, before applying the filter, you need to find the Fourier transform of this image. F of xy will be converted to f of u comma v. But when you apply here, what happens here is f of u comma v, Fourier transform of this f of x comma y. You cannot express it as the separate products of the Fourier transforms of I and R, because you cannot, the Fourier transform don't have such a property, and we need to have a linear atmosphere. So what we are doing here is, instead of expressing this as a product of two terms, you will express it as the sum of two terms. For that you are taking the natural logarithm of f, that is called z. So it will be ln of I plus ln of r. Now you apply the Fourier transform of z, so that the Fourier transform of this component plus Fourier transform of this component, that is written over here, and we will represent the new equation as z of u comma v, which is the Fourier transform of z, and fi of u comma v is the Fourier transform of the natural logarithm of I. Fr is the Fourier transform of the natural logarithm of r, that is the reflectance. Okay, now we can apply the filter because the equation is now made linear. It's a sum of two components. Now we have the filter capital H. Actually, the filter is small h of x comma y. You have found the Fourier transform of that filter, which is capital H of u comma v. Okay, the filtering convolution operation in time domain is equivalent to multiplication in frequency domain. So capital S of u comma v is equal to h of u comma v into z of u comma v. Substitute for z of u comma v from here. So your equation is this one. Okay, this is now the filtered part in frequency domain. You need to find the filtered part in time domain, or mean spatial domain. For that you take its inverse Fourier transform. It is the inverse Fourier transform of this component plus this component. Okay, you write the inverse Fourier transform of this part as I dash of x comma y. That is the filtered illumination component in spatial domain, and similarly filtered illumination component in filtered reflectance component in spatial domain. So the new equation is s of x comma y is equal to I dash plus r dash. But still this is not the complete, because initially you have taken what is called the natural logarithm. You have to take the inverse of natural logarithm using e. So take e raised to s of x comma y, that is e raised to I dash into e raised to r dash, that is g. So this is the finite filtered image, which can be expressed as I0 into R0, where I0 is e raised to I dash, R0 is e raised to r dash. They are the illuminance and reflectance components of the output processed image. And this operation is now represented in the form of a block diagram. Initially, you have the image, take its natural logarithm, find the DFT. Okay. Then you apply the filter, inverse DFT, taking the inverse of natural logarithm, that is exponential, to get the final image G. The system is called homomorphic system. Okay, and so this is the procedure in homomorphic filtering. And next thing is what you need to know is what is a filtered function. You have explained the procedure. Next, you know what is H, or how do we select that filter. In order to select such a filter, you must know one thing, that uh, the image contains, now an image is expressed as a product of illumination and reflectance. So the illumination component of an image represents the slow spatial variations, which means that such components will be associated with the low frequencies present in the image. So if you take the Fourier transform of an image, the low frequency part represents illumination component. Okay. And similarly, the reflectance component tends to vary abruptly. So reflectance components are associated with high frequencies. So there is a way to separate your high frequency components and low frequency components roughly using this illumination and reflectance modeling. Okay, so this is actually a good deal of control using can be gained over this illumination and reflectance components with a homomorphic filter. Next, let's see how to select h of u comma v. A typical equation for this is shown over here. This is the shape of that filter according to this equation. Here you consider this part 1 minus e raised to minus a quantity whose shape will be like this. This is just like the equation of a capacitor charge exponentially 1 minus e means finally it gets saturated. So you are taking two values gamma L and gamma H in such a way that gamma L is less than 1, gamma H is greater than 1. So gamma L and gamma H are the two parameters associated with the response of the filter for low frequencies and high frequencies. So in this equation, this D0 is called a particular cutoff frequency, and D represents what is called your it's actually cross-sectional view. It represents the radius. So when your D is equal to 0 means you are at a low frequency. This represents a frequency D. When D is equal to 0 means you are at low frequency. So e raised to 0 means you have 1. So 1 minus 1 is 0. So this part is now 0. 0 into this part is 0. Remaining part is gamma L. Okay. So at D is equal to 0, you have h of u comma v equal to gamma L. That is obtained here. This is your frequency axis D. D0 angle, your h of u comma v is equal to gamma L. And as you increase D, you can see that h of u comma v increases exponentially initially. Initially, it has an exponential manner. And finally, for D, for very high values of D, I mean high frequencies, this quantity will be negligible. For high values of D, this part will be very small compared to 1. So you can make this part 0. So the remaining part is 1. So h of u comma v is equal to gamma h minus gamma l plus gamma l. Gamma l and gamma l gets cancelled. H of u comma v is equal to gamma h. So finally for high values of d, the response will be gamma h. In between you have a variation like this. Okay, so our aim is to make the response of this filter towards low frequencies. That is, low frequency means illumination. It will be equal to gamma L. And for high frequency, that is for reflectance, the response will be gamma H, that is greater than 1. So for illumination part, you have a attenuation, and for reflectance part, you have a gain. So our aim is to what we're doing here is by attenuating the contribution. This is attenuating the contribution made by low frequencies and amplifying the contribution made by high frequencies. This is the net result is simultaneous dynamic range compression and contrast enhancement. You are highlighting your higher frequencies and you are attenuating your low frequencies. So this is the net result is dynamic range compression and contrast enhancement. Dynamic range compression you are getting because you are taking natural logarithm and all. Okay, so finally this is the result. An example for this application is discussed here. That is, you can read this. A typical example is shown here using a medical image, positron emission tomography image. Okay, so you go through this example, then you will get more idea. So that is about the homomorphic filter. Okay, next comes image averaging. Actually, this comes under the topic called arithmetic operations. You have different arithmetic operations. Here f and g are two images. You can add two images, subtract, multiply, divide, etc. And out of this, what we need here is the first two, addition and subtraction. And this comes in your third module, image subtraction and image averaging. These are the two topics which were not covered. Okay, that we will discuss now. So in you are using these two equations. Okay, first let us see image averaging. So you all know image averaging is just like a low pass filtering operation where you can remove the noisy part. You can remove high frequency details. We call it as an image. So to explain this is a mathematical explanation to how image averaging reduces noise. You are taking an image f is your image, f is your original image, and you are adding a noisy image. I mean noise, this is your noise. Adding this and this will get a noisy image G. Okay, and the features of G, the noise is that noise is uncorrelated and has zero average value. Okay, so this is the equation, not this equation number 1. Now the objective is to reduce the noise content by adding a set of noisy images. So you are going to create a number of noisy images like G by adding different noises. Not different noises in the sense the characteristics of the noise is same, but you are adding it. Suppose at a certain point of time you take eta, it has got a typical set of random values. For the second time or after some time you are again considering the same noise, but the values will be different. That is called, first you take eta 1, then you have eta 2, eta 3, eta 4, etc. For all these noises you have the same characteristics, but the values are random, so it may change. So likewise you have created k such noisy images, set of gi, and you take the average of all these k, that is g bar, that is written over here. Then you take the expected value of g bar. Gi is the, you know what it is, gi, f plus eta I, and g bar is 1 by k f plus eta I, summation over k. Expectation of, you are going to find the expectation of g bar. and before that you must note this E of A plus B equal to E of A plus E. So we just substitute G bar here and take its expected value, we will get this. Since f is a deterministic signal, its expected value will be same as f, and you have taken that mean of the noise is 0. Okay, now expected value of G bar will be 1 by k sigma equal to k f. You are adding f k times, so you have k into fx will be the sum. Now 1 by k is there, k gets cancelled. So the expected value of G bar will be equal to f. This is one intermediate result that you must remember. Next we take variance of G bar. It is indicated as sigma square gx. How do you find the variance? This is equation to find the variance of G bar is in this equation. G bar minus expected value of G bar x whole square. Okay, next we will expand this square. These are the four different terms when you take the square. Again, you have split the different terms like this. Here, expected value of x square of x comma y is f square x y itself, because this is a deterministic one, and expected value of this quantity means 2 is constant, you can take 2 outside, and expected value of a into b is expected value of a into expected value of b. So expected value of f will be same as f itself. So that is why you are getting like this 2 into f into expected value of G bar, and you know expected value of G bar as f itself, so it will be minus 2 f square. Now the rest to find is the expected value of G square of G bar square. So substitute for G bar square, it will be like this. You have an equation like this. I'll expand you putting substituting for the variable I varies from 1 to k. You are adding f k times, you have k f x, then eta 1 plus eta 2 etc, taking its all square. When you find okay, next to find the expected value of G bar square, then finding the expected value of 1 by 1. Before that you need to expand this square. How can you expand this? You have a plus b plus c plus d, like that you have a or a1 plus b, a1 plus a2 plus a3 plus etc to a whole square. We will get as a1 square plus a2 square plus a3 square plus a4 square plus a1 a2 a1 a3 etc. So finally we will have the square of individual terms plus the product of these different terms. So when you find the expected value of f square, you have f square itself. So k square into f square here. Then expected value of the square of this, expected value of the square of this, and expected value finally square of this. ഇത് മാത്രമല്ല ഇതിന്റെ കൂടെ കുറച്ചും കൂടെ ടേംസ് വരും, just like expected value of this into this, expected value of this into this. Since your noise is uncorrelated, all such terms will be made 0. Like expected value of f into eta 1 will be 0. Expected value of eta 1 into eta 2 will be 0. Okay, only these terms will get remained. And what is this? Expected value of eta 1 square x means this is the second order moment of eta I. Since this has got 0 mean, this second order moment will be same as the variance of this part. So you are making or you are considering the variance of your noise term as eta square, sigma square eta. എല്ലാ നോയ്സിനും ഇതെല്ലാ കോമ്പോണൻസിനും സെയിം വേരിയൻസ് ആണ്. So you can treat these all as same values, and you are adding all these together. You have k into sigma square eta. പുറത്തൊരു 1 by k square ഉണ്ട്, cancelling 1 by k. So this will be your expected value of G square of x. ഇത് ഇവിടെ നമ്മൾ സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്ത് കൊടുക്കും in this equation. So finally you will get the variance of g bar as 1 by k sigma square eta, or the standard deviation, like this. And as k increases, what happens, this value gets diminished, so the variance is made zero. If variance is made zero means all the values are deterministic, there is no randomness, so noise is removed. So when you add a large number of noisy images, you are getting you are adding a large number of noisy images. Here we are, sorry, this is your addition of noisy images, and you are taking its average. If you have k as a very large value, what happens here, the expected value of this will be equal to f. അതായത് ഒരുപാട് നോയ്സി ഇമേജുകൾ എടുത്ത് ആഡ് ചെയ്ത് കഴിഞ്ഞാൽ ആ കിട്ടുന്ന ആഡ് ചെയ്ത് കിട്ടുന്നതിൻ്റെ ആവറേജ്, അതായത് ഇതിൽ ഒരുപാട് നോയ്സി ഇമേജുകൾ ആഡ് ചെയ്തു, എന്നിട്ട് ജി ഐ ആണ് നോയ്സി ഇമേജ്, എന്നിട്ട് അതിൻ്റെ ആവറേജ് എടുക്കും, ദാറ്റ് ഈസ് ജി ബാർ ഓഫ് എക്സ്. ഈ ജി ബാർ ഓഫ് എക്സിൻ്റെ എക്സ്പെക്റ്റഡ് വാല്യൂ എന്ന് പറയുന്നത് നമ്മുടെ ഒറിജിനൽ ഇമേജാണ്. മാത്രമല്ല ഈ ജി ബാറിൻ്റെ വാരിയൻസ് എന്ന് പറയുന്നത് ഇതാണ് വാരിയൻസ്. ഇതിൽ കെ ഇൻക്രീസ് ചെയ്ത് കഴിഞ്ഞാൽ ഈ വാല്യൂ സീറോ ആവും, കെ വളരെ ഹൈ വാല്യൂ ആണെങ്കിൽ. നമുക്ക് ഇമേജ് ആവറേജിങ് mathematically it will remove the noise, additive noise from the image. Only if your noise is additive, zero mean uncorrelated. Okay, next ഒരു എക്സാമ്പിൾ പറഞ്ഞിട്ടുണ്ട്, just go through it. Next അതിൻ്റെ വേറെ ഇമേജ് സബ്ട്രാക്ഷൻ ആണ് പറഞ്ഞത്. You are subtracting two images f and h. അതിനൊരു എക്സാമ്പിൾ ആയിട്ട് ഒരു മെഡിക്കൽ ഇമേജിൻ്റെ കാര്യം പറഞ്ഞിട്ടുണ്ട്. സപ്പോസ് you are undergoing patient's body, or certain region of patient's body has been undergone for a medical checkup. So what you are doing here is, first you take the x-ray of your patient's body, that is called a mask image. Then you take the live image of your patient's body after injecting a X-ray contrast medium. The procedure consists of injecting an X-ray contrast medium into patient's bloodstream, then taking a series of images called live images, which is denoted as F. Initially, the X-ray image എടുക്കുന്നു H. പിന്നെ X-ray contrast medium inject ചെയ്തതിന് ശേഷം ഒരു image എടുക്കുന്നു, that is F. അത് രണ്ടും കൂടെ subtract ചെയ്യുന്നു. Now you can see the difference, what happened. The net effect of subtracting will be the difference between f of xy and h of xy appear in the output image. In the example, this is your mask, this is your live image. After injecting the contrast medium, you subtract these two, you will get an image like this. You know, enhanced what you can see here is how the injected medium gets traveled through your blood vessels. ഇതിനകത്ത് മീഡിയം ഇല്ല, ഇതിനകത്ത് മീഡിയം ഉണ്ട്. മീഡിയം ഉള്ളതും ഇല്ലാത്തതും തമ്മിൽ സബ്ട്രാക്ട് ചെയ്യുമ്പോൾ ഇതൊരു ലൈവ് റെക്കോർഡിംഗ് ആണെങ്കിൽ you can see how this injected medium gets traveled through your blood vessels. This is normally used in angiograms in order to find blocks and all. Okay, so that is the application of image subtraction. So that's all about the discussion of image averaging and subtraction.